Her current research focus is on biodiversity, biological activities, and chemistry of marine sediment, derived actinobacteria from Philippine archipelago that could one day help to find new antibiotics. Our group explored the Philippine archipelago for the presence of promising actinobacteria found in the marine sediment samples collected in different islands in the country. Our laboratory now houses a library of more than 3,000 highly diverse marine sediment-derived actinobacteria that serves as biobank for drug discovery research in the country. Right now, she's also the project leader of Class Lunas for Visayas, and she has established that a laboratory that is funded by the US, and I think she will speak some more about that in her talk. So may I call on Dr. Lavinia for the first lecture.
Good afternoon. I hope you are still awake. Yes, so I wake up this morning at 3 a.m. to catch my flight to Manila. So please wake up just like me here, all right? Okay, so what I'm going to talk about is a combination of the omics that was presented this morning, and of course the metabolomics. So this is genomics and metabolomics, and this is our recent result of our work in the past 2 years that we've been working at University of San Agustin. Why is it that I think this is not working? Yeah. Stop muna yung time. Wala rin. No battery. Okay, so why do we need antibiotics more than ever? It is not a cliche, it's always there, just like coronavirus, but it is not being hyped by the media. But you can see here that it is globally important because of this multi-drug resistant, there is no drug right now, or the drug is limited to cure them. And so, this the war against these microbes is because of the strains of bacteria we call as superbugs that are clinically resistant to several available antibiotics. And if you look at by 2050, more than 10 million people will die because of multi-drug resistant pathogens. And what's surprising here is in Asia alone, there are about 5 million of this death that is being predicted because of multi-drug resistant bacteria. And so therefore, there is a void in looking for a drug against this multi-drug resistant bacteria. So I am a pharmacist by profession, and so therefore I'm very interested at looking for new antibiotics. If you look at this area here, the discovery and development, there is a void. It's because manufacturing of pharmaceutical companies doesn't want to invest more on this, because they would rather invest on drugs that treat lifestyle diseases because the return of investment is very fast. Unlike with antibiotics, there's only 5 or 7 days of treatment, and then after that, that's it. And so there is no investment there, and a return of investment, and so therefore, the R&D in pharmaceutical company block this type of undertakings. And now, academic institutions are looking into this because this is very, very important. And so, we all know that we have bacteria in the soil that produce this metabolites. These are called actinobacteria. I consider them as the smartest chemists produced by nature. They are very small, but they are incredible because they are producing this biosynthetic machinery that we could engineer later on to produce these different types of compounds. And looking back at the history, actinobacteria produces this popular antibiotics. Erythromycin, for example, rifamycin, vancomycin, they all came from soil actinobacteria. And in fact, if you look into erythromycin, the history of this started in Iloilo City. It is the soil from Iloilo that they got this bacteria that produced this erythromycin. That's why the brand name is called Ilosome, or they call it before Ilotizone, because of Iloilo City as the original source of the antibiotics. And so therefore, what's the difference here, or what's not good in here, is this is done by foreign scientists. The IP is not owned by the Philippines. And so therefore, it's our natural resources that is used to treat this disease. And so therefore, when I came back to Philippines, I said, I will not, this situation will not happen ever again. Because we will look at it in a way that discovery uses the Philippine resources at the same time done by Filipino scientists. And so therefore, I'm looking right now at another niche, which is the marine environment. I love the ocean. I live in a town where my parents' house is only 10 meters away from the shore. And I always love that. And so I'm always fascinated by the ocean. And I'm looking at this time the sediments from the ocean. If back 50 years ago, they're looking at the terrestrial soil, I'm now mining the marine sediments. So if you look at the marine sediments, there's always a delay here. Okay, so the marine life is very abundant with diversity. And if you look at 1 ml of water, it contains about 1 million microorganisms. But if you look at the sediments, there's about 1 billion of these cells per gram of the sediment. We thought that sediment is there's no life in there, but actually there's life. So they are there because they have surfaces that these bacteria can attach. But the next. Okay, so marine sediments is a promising niche for drug discovery. It's salty, and it's cold, it's dark, and it is very diverse in microbial community. I'm not looking into the microbiome of the sediment. My work is more targeted approach. I'm interested in only one type of bacteria, family of bacteria, and nothing else. That's why our method is very selective, because I'm particularly interested in one type of bacteria, and also it is culture dependent. So if you look at this, it looks like a rock, right? But actually this is not a rock. This is a grain of sand, a scanning electron microscope. But if you look at that area and then expand it 50,000 times, you will see life. There's life in that one grain of sand. There's spores and filaments of this bacteria that adheres on the surface, and this is something that we could exploit in our work in finding new drugs. So these are examples of the antibiotics that we isolated from different types of bacteria, isolated from marine sediments all over the world. This one is from the Pacific Northwest sediment. Another one is an antibiotic from Papua New Guinea. We call this pedanamide. It's a very nice short tetrapeptide. We continue our work. When I say continue, we are husband and wife team. We are doing drug discovery program, and we are looking into marine microbiology, plants, marine invertebrates, and uses these different strategies to find that compound that can cure different types of diseases. So we look into, can you go back? So we have this metabolomics, and we have also this genomics. So for the last 2 years, we had the opportunity to explore the States of America, but the University of San Agustin is a small university, Catholic private university, and this is our Center for Chemical Biology and Biotechnology. Is only 1 year old. And Now, I'm going to take you to the famous Tubataha Reef in Palawan. So my team went to Tubataha National Reef. It's one of the best opportunity I had. So we were aboard a MY Palau Sport. This is our research vessel. So I'm the only woman in the team, and we among the men. So we were there for 7 days, and back in the States, we are using an automatic robotic system as a core sampler. Here in the Philippines, I can do that. So I sketch and let somebody did it for us, backyard na gumagawa, fabricated for us, and then boom, we have this. So there is already a utility model. So we have 1 meter of that core, and so therefore, we got the core sampler and then bring that to the lab. So in 2017, we were able to go to different islands in the Visayas area, Western and then Central Visayas. In Negros Oriental, in Apo Island, one in Bohol, Bagbatan Island in Antique. In this part, we also have in Crocodile Island, Aklan near Boracay Island. We have in the Nugan Island in Negros Occidental. We also have one in Antique, in Mararison Island, and also Nongas Island in the tip of here, fronting the Sulu Sea, and Capiz, and also we have Antique. During this time, I'm going to tell you, this is one of the best part of research, right? But the most difficult part of research is to get the prior informed consent. It took me 6 months to get a prior informed consent, talking to the barangay, the LGU unit, and this is one thing that I think MAST should help the researchers to get this prior informed consent, so that their research there will be no delay. So this is the second year. We went up to Batanes Island, Occidental Mindoro, Camarines Norte. So there were about 23 sites all over the Philippines. And this was in 2018 to 2019. So, next slide please. So we have this about more than 3,000 of these diverse bacteria, actinobacteria. I haven't seen that diversity when I work with microorganisms from Bahamas or Papua New Guinea. These are entirely different types of bacteria, and so the diversity there is very, very high. And so this is considered as a drug discovery biobank of the Philippines. Anyone can collaborate with me. I'm very open. So as long as we look into new drugs and for the treatment of antibiotics. So we have 3,371 of this. The most prevalent actinobacteria are from Negros Occidental Island, followed by the Southern Antique, and then followed by the Sulu Sea. So this is how we did our approach to find a new metabolite. So we did our in vitro bioassay, we did the genomics, and then did the metabolomics. So our target is not just an ordinary clinically available pathogens, but these are multi-drug resistant pathogens called escape. And these are all in here. So escape. So you have to remember that microbiologist tayo, kailangan natin yan malaman, right? And so therefore, we have different types of screening full platforms. We have initial screening, secondary screening, and then we have the confirmatory screening. And we now have, we now have about 38 lead isolates that we can say we can ferment this and then grow new natural products. But what really guided us, aside from bioassay to find new novel entity, is to work with the genomics and the metabolomics. The traditional is the bioassay, blah, 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 but what will result with that is the rediscovery of the same type of antibiotics. We want something new. And so therefore with the omics platform, we're able to help us to detect where can we, one particular group of organisms to look into. So Next. So we have in here, so we have the genomics. Of course, we have to know what is in there. So we did the phylogenetic gene marker, but we also are interested with the biosynthetic gene clusters because I'm interested on the machinery of how these antibiotics are produced so that we can engineer it in the next phase of our project to provide more amount of this material. And so therefore, these are the 169 majority of our bacteria, and these are all belonging to the genus Streptomyces. So you will see that there are about 8 different clades we have identified. So we did not just sequence one area on the 16S. This is the whole complete 16S, 1500 base pair. And so therefore we were able to identify what the similarity between these different types of organisms. And we found that mostly 29% are Parvulus, Roche, and Cilis, and some of that are in here. And if you look into here, in this part, next, we have identified about 4 novel Streptomyces species. Never been found, in no similarity in database, and that we are very excited. We already have the complete genome of these 4 different types of novel organism, and now we are mining their biosynthetic gene cluster, and it's very exciting to see enzyme and biosynthetic gene clusters there that expresses different types of novel bacteria. So, with environmental point of view, I want you to look into this area here. So these are all the sampling sites here, and these are the different bacteria that we're able to isolate. And we have a diversity index that you can point them at here. So the highest diversity is number 10, and that is northern Antique. Most of the samples facing the Sulu Sea has a lot of diversity. However, if you look at number 6 here, this is Aklan. This is where we got samples near Boracay Island. The diversity is very low, and we only have one type of Streptomyces there. So, and it's not only Boracay that we've seen, but there are also Central Visayas. This is a near famous beach resort in Paglao area. So what does it tell us? It's more of the anthropogenic activities that dictates the diversity of these different types of Streptomyces. So we have 8 lead compound, a lead actinobacteria, and we have found kung saan sila makikita. In Tumataha, this is in Western Antique, Northeastern, dito sa Negros Occidental. This is in Apo Island, and then this is in Camarines. So it's very exciting, and I am not going to disclose what are these different types of Streptomyces. So we look into the small metabolite, okay? So kumbaga, meron kasi machinery, that's why I call them small but incredible, because they have these biosynthetic gene clusters. So these are modules that they have in them that create these different types of molecules. For example, PKS1, the very popular one is the erythromycin that they produce. It has these 4 different modules. Another one is PKS2. These are the typical common antibiotics that are produced by PKS2, tetracycline, and the anti-cancer doxorubicin. And so therefore, we sequence and amplify this biosynthetic gene cluster, and we found that most of them has the PKS1 module and also the PKS2 module. But look at this one here. There's only one type of PKS present there, and most of them also have the NRPS or the non-ribosomal gene cluster. So looking at the cytoscape that Dr. De Los Reyes pointed out, so you have to look into different types of platforms. These are freeware, so you please use that, study that. What we found here is This is the target organism. These are the machineries that produces the antibiotics. So we have found that if there are two of this machinery present, their activity varies from 61 to 91%. And what's interesting is this type of organisms that they only need this type of PKS, but they have a very high activity. What's also surprising to us is we have this cluster 4 and cluster 3. They do not have PKS, but they have PKS, but they have no activity against this organism. So meaning, even though they have machinery to produce this very elaborative chemical entity, the compound does not target the S aureus. This one is another interesting one. This is the PKS2. You will see that there are 3 clusters. For example, this group here, there are 3 machineries needed to produce its activity against this. But this cluster has only 2 of the machinery. This one have 1 machinery needed to target this. But how about this? This is very interesting because they don't have the machinery just like this, but they are very active. So we're looking at that right now. Could this be something new or something different? So then we go to the metabolomics. The metabolomics uses LCMS. Okay, so we do LCMS, we do GNPS, and also we do a lot of multivariant analysis. So this is where microbiologists, please be a statisticians, okay? So because we have a big data, we have to understand what it is in there. So if we are looking at this area here, the 16 SS, isang tubog lang sila. But actually the metabolomics says it's different because this is how they look like in the metabolomics. They are so diverse. But here, another one. So you will see that these are how their dendrograms is different. Though the 16S, yes, they can tell us the phylogeny, but the metabolomics is the one that dictates, even though they are the same, but the metabolomics is different. So we looked into this. So it tells us that these are the active isolates and these are the inactive isolates. When we look at their metabolites, these are metabolites produced by both the active and inactive. These are the compounds produced by inactive isolates, but these are the compounds produced by active isolates. So ito po yun ngayon yung hinahabol namin because this is something new. Alright? So this is a ongoing work in our lab. So these are examples of our work that these different types of metabolites are produced by one single isolate, but there are also some that are produced shared by everyone. So what do we do here is we do MSIMS analysis, and we found that, for example, can you go next? These are the compounds that we produced. The metabolomics can identify what are the compounds that these isolates are produced. Another one, for example, we have these different types of compounds, so we do the MSIMS analysis. These are known. That's why I'm very happy to share it with you, because the unknown, I'm not going to share it with you, or something new. So these are all known compounds that are produced by the different types of bacteria. So, so in the end, can you go? All right, so drugs from the vast Philippine Marine Sediment-Derived bacteria offers economic and healthcare benefits to the society. Philippine Marine Sediments are very rich, so konti lang po yung kinuha namin. So you still have a lot of playground to go and then find these new different types of organisms. So one part of our project is we went back to the community to tell them a science-based policy. We went back to the community where they gave us a go signal to get the samples. And natuwa sila because they are aware that this is what's happening. In fact, they say, kayo lang po yung bumalik from the many researchers that asked permission from us. So we went to Bataha, another one, we went to Occidental Mindoro and Apo Reef. We also went to Pojada Island in Davao Oriental, in Lahanosa Island, Surigao del Norte, and Apo Island in Negros Oriental. And recently, we gathered all people in the province of Panay to have a science policy recommendation, and they were very happy and they have included that in their work. So these are the policy recommendations that we have given it to them, and they're very happy about that. And then also the pollution, so recognition of the marine biodiversity. In fact, yung Dalisay and Antique already have a resolution of gating the area and made it as a marine protected area because of our results. And we're very happy about that. And so therefore, to end, I would like to acknowledge the Balik Scientist Program of DOST, University of San Agustin, the National Research Council of the Philippines for the funding, and DOST, and these are my research team. So thank you very much for your time.
Thank you very much, Dr. Lavinia and Dr. Dalisay. Nagising naman kami sa lecture mo. So the floor is now open to questions. Yes, Divine. Bida-bida ka na.
Dr. Dalisay, magandang hapon po. I was so amazed with the background that you have related pertaining to your early childhood na nakatira lang sa bahay na ilang metro na ang layo sa dagat. Yung po bang inspirasyon na yun ng inyong kabataan, pati na po ng inyong biological background has been highly contributory and instrumental for you to pursue this kind of studies at how do you encourage po yung mga kababayan nyo na makikollaborate sa inyo? Salamat po.
Okay. So, yes. So, my childhood was the one that it takes me to love marine science. So, kaya nga, I was bullied when I was in high school dahil itim ko. Dahil I was always in the ocean. Itim ko daw. So, and anywhere I go, yung one requirements ng university is malapit sa dagat. I went to UNSW sa Sydney, malapit yan sa Pacific Ocean. And the University of California in San Diego, malapit din sa ocean. And British Columbia, University of British Columbia, malapit din sa ocean. So when it comes to collaboration, lahat tayo dito microbiologists. If you have an interest, for example, ano lang kaya ng lab namin are antibiotics, looking for antibiotics and anti-cancers. If your lab is capable of have a platform of assays looking at, for example, leptospirosis, malaria, virus assays. So I can, yes, in different, kahit sa mga tanim, because these are highly saline na organisms. So marang mga drought na mga sensitive na mga taniman dyan, we could collaborate, perhaps we could collaborate on those matters. So we have a library not only of a bacteria, but we have a library of thousands of extracts. Ready na po yun na pamigay, right? So kung nagko-collaborate ako outside, why not collaborate dito, right? So just send me an email or sometimes after this, talk to me, and then we could expand this drug discovery program tinayo namin sa San Agustin.
That's a very good offer. Any takers? Okay, Dr. Concepcion.
So I just wanted to know how you delete the genes for those enzymes so that you focus on ethanol production and secondly, how production of butanol affects the E. coli. Is it toxic to the E. coli? So is there culture design such that we are able to remove butanol? So is there a bioreactor with it? Can you tell us a bit more about the engineering part of it?
Yes, ma'am.
See, you have something.
Thank you, ma'am, for the question. So, for the addition, we just did the simple division, just the normal site-directed division of feeds. And we found out that actually the 1-butanol is toxic to the cells. So when the production stops, that means it reached the toxicity level is around 1 gram. For cyanobacteria is around 1 gram per liter. So when it reaches that, then it stops the cells dying. So when after several rounds of strain improvement, we found out that the cyanobacteria won't live anymore. So what we're trying to do is to increase the tolerance of cyanobacteria E compared to 1-butanol. So that's the first step that we do. So that's also a possibility to try to extract the 1-butanol and then in a continuous culture.
So at some point, the butanol might serve as an inhibitor, okay, in the genetic enzyme level. So I'm just curious whether that happens. Okay, I'll just ask a question to Doralyn because we also have 4,000 bacteria, so we should collaborate.
I know the two of you should collaborate. One is a marine sediment, one is
We
water.
invited her to be a faculty in MSI, but no, she has to build USA out of the USA. So she's doing a great job. So you were talking about antimicrobial resistance, and that's really a major problem. So we actually have compounds already patented that are antibiotics to MRSA, and also now to gram-positive, and then gram-negative Pseudomonas aeruginosa. So published and then patented. Okay, so also from bacteria. Now, thing is, we have to understand the mechanisms of antimicrobial resistance. Why? Why is it now resistant? For example, MRSA. Okay, the model for SA actually is S. epidermidis also. And one major mechanism of resistance is the formation of a biofilm. So it really, learns how to become not a unicellular but a multicellular organism as a kind of a shield. No? So you form a biofilm and it becomes like a metazoa. Anyway, do you have assays that measure inhibition of biofilm in your Staph aureus, or is it escape as a planktonic tax? Because we also run escape routinely.
So a very nice question. Yes. So we do not have an assay for biofilm. I will send it to you definitely. Yeah. So the extract and some of the pure compounds that we can check.
May I recognize the lady over there?
I'm Rudy from UP Visayas, and I graduated recently lang for my PhD. I also engineer E. coli. So my question, or curious lang ako, pwede ba kung I engineer E. coli to produce ethylene glycol, which is antifreeze chemical sa mga car engines. I also engineer E. coli. I also have a strain for glycolic acid production and for xylitol production. So we have a problem actually sa engineered strains namin because we are just using conventional methods, everything. We have not yet tapped on the omics side. So I'm just curious, if I want to subject my strains on metabolomics, can I send it to UNLV or
You're over, you're near, Doralyn's not nearer.
But she said that she's just going to collaborate with people inclined to antibiotic discovery.
So, okay, thank you very much. So we would welcome collaboration with other universities. So probably you can send the samples to us. I can analyze the primary metabolites and she can analyze it. So we're open to you just send the proposal or write the proposal and then we can talk about it.
Just a quick question. Follow up. How long does it take from this study when you make to engineer the system to figure out they lack something to repair it to get the performance?
So this one took around like more than 5 years. So
From the engineer.
from the engineering, it took like 3 years. Three years, and then it was engineered in UCLA. To fix the problem, it took us like 2 years.
To diagnose the problem.
To diagnose the problem, 6 months. Six.
So the metabolomic diagnosis
Yeah.
is 6 months.
So especially if the answer you can find easily, then you can do it in like 3 to 6 months.
I have a basic question to antibiotics researcher. I was a researcher long time when these ladies are still in their high school. And we have also at biotech thousands of actinomyces from the soil, but we haven't been doing we have the classical ways of doing it. And I have heirs to those cultures, and I hope they'll be doing something about it. Anyway, what's the future of all these antibiotic forming strains? The antibiotics they have formed. Will they find themselves in the factory, in the pharmaceutical industry? Where will they go? The question I asked when I started working on antibiotics, and still asking up to now. So these ladies may be able to answer it.
2 years ago, the European Union had a program. Okay? 2 years ago, the European Union had a program, and we're trying to catch, that deadline. They had reduced the MIC from 32 micrograms per mil to 65 micrograms per mil for a compound to show antibiotic activity in an animal model for a single drug-resistant, preferably gram-negative infection, the pathogen. So right now, our compounds are in that stage where we're producing milligram quantities of it, okay, in culture in our lab, and we're doing animal model for this, okay? So we have the bacterial pathogens that we are injecting into the leg or the foot of the mouse, and this is our major priority now in our lab.
So our lab in the University of San Agustin is not only capable of isolating these new antibiotics, but we are also at the same time doing toxicity testing, because we rather fail now than fail later. Meaning, hindi namin gusto na i-advance ito an animal model or a human trial without identifying whether this is toxic in the liver cells, kidney cells, and cardiac cells. So, the end product namin sa University of San Agustin have an antibiotic that we know that it's active against the target cell, and we know that it is safe in vitro sa liver cells, kidney cells, and then the heart cells. We cannot manufacture it just like the manufacturing pharmaceuticals. But what we hope is that we could license it that we could patent it and let these big pharmaceuticals buy the license to us. Anyway, yun naman hinahanap nila eh. They scout for startup companies, and then once there is something that is already in the pipeline, they buy the company and then develop it individually. So we are hoping na yung erythromycin story will not happen again. And so therefore, yun nga, the community is very excited about our work dahil sabi nila, this can really help us here in case na